previous session we have seen formula for Fourier transform, inverse Fourier transform, as well as we have seen one example where we have determined the Fourier transform of the given discrete time signal. In today's session we will be discussing the linearity property of Fourier transform. So as per Fourier transform, the Fourier transform of discrete time signal x of n, so it is simply represented as capital F of x of n, and it is denoted as capital X of omega, and the formula for this same is summation n is equals to minus infinity to infinity x of n into e to the power minus j omega n. Okay, so this formula we have seen in previous session. So as per the linearity property of Fourier transform, if there are two discrete time signal x1 of n and x2 of n with their respective z transform x1 of omega, Fourier transform x1 of omega and x2 of omega. So if x1 of n has the Fourier transform x1 of omega and x2 of n has the Fourier transform denoted by x2 of omega, then as per the linearity property, the linear combination of x1 of n and x2 of n, okay, that is a1 x1 of n plus a2 x2 of n as the Fourier transform, which is nothing but the linear combination of their respective Fourier transforms. Okay, that is a1 x1 capital x1 of omega plus a2 capital x2 of omega. Okay, so that is as per the linearity property. So the Fourier transform of a linear combination of two or more signal is equal to the same linear combination of the Fourier transform of individual signals, right? So it is somewhat similar to the linearity property of the Z transform, okay, that we are discussing the Z transform topic, right? So this linearity property of Fourier transform, where we have taken the two signals, that is x1 of n and x2 of n, with their respective Fourier transform denoted as x1 of omega and x2 of omega. So the linear combination of these two signals has the Fourier transform, which is nothing but the Fourier transform of their respective Fourier transform. Okay, linear combination of respective Fourier transform of these individual signals. Okay, so we'll try to solve one example here by applying the linearity property. So here we have to determine the Fourier transform of the given signal x of n is equals to a to the power mod n. Okay, so where a is between -1 to 1, that means it can have any value between this range. It may be 0.24 or maybe 0.1 or maybe 0.9 and so on, right? So this given signal, input signal x of n, can be represented as two different signals x1 of n and x2 of n. So how we can represent it as? So the given signal x of n can be represented as it is x of n is equals to the linear combination or sum of two different signals, that is x1 of n and x2 of n. Okay, so where this x1 of n will consider as it has been taken as the mod of n. So if you want to remove this mod of n and represent the given signal as the summation of these two different signals, so first we'll take it as x1 of n is equals to a to the power n, or it can be 0, right? So it will be a to the power n, so the power of a will be positive values of n, okay, will exist in the signal because the mod has been taken here. So it will be true for n greater than or equals to 0, and it will be 0 for negative values of n, that is for n less than 0, right? So this is about x1 of n, right? So x1 of n will be a to the power n. So this a to the power n will exist only for positive values of n, right? So similarly you can represent it as x2 of n when n is negative, right? So for that purpose you can take a to the power minus n and 0 otherwise. So this will be again true. So here we need to take the value of n negative, so that the value of n, if you are taking negative, so minus minus will be plus here, right? So this will be true for n less than 0, that is for negative values of n, and it will be 0 for positive values of n, for n greater than or equals to 0, right? So these will be the values of x1 of n and x2 of n. So if you are combining, so it will be simply representing this a to the power mod n, because we have already specified the values of n here, right? By using the conditions, right? So whenever you are taking x1 of n and x2 of n, so the power of a will be positive always, okay, because here mod is there, right? So this is how we can represent this x of n. So by using the Fourier transform and linearity property, now we can identify the Fourier transform of this individual signal, and to get the Fourier transform of x of n, we'll simply sum the Fourier transforms of x1 of n and x2 of n, right? So by using Fourier transform, the Fourier transform of x1 of n will be represented as simply x1 of omega. So it is nothing but the Fourier transform of x1 of n, right? And it will be equals to summation n is equals to minus infinity to infinity, right? So x1 of n into e to the power minus j omega n, correct? So x1 of n, we have taken it as a to the power n, right? So summation n is equals to minus infinity to infinity, so it will be a to the power n into e to the power minus j omega n, correct? So as per these limits on n, so a to the power n is exist only for n greater than or equals to 0, otherwise it is 0, right? So we can modify these limits instead of taking it from minus infinity to infinity, because for negative values of n this value is 0, right? So instead of taking it as minus infinity to infinity, we should take it as 0 to infinity, okay? So it should be 0 to infinity. So I will rewrite here. So n is equals to 0 to infinity e to the power n e to the power minus j omega n. So from e to the power n e to the power minus j omega n, you can take n common, so it will be a into e to the power minus j omega whole raised to the power n, right? So we have seen the infinite geometric series, right? So n is equals to 0 to infinity a to the power n is equals to 1 upon 1 minus a, provided mod a less than 1, right? So here we can simply write it as what? 1 upon 1 minus a e to the power j omega n, okay? So 1 upon 1 minus a into e to the power minus j omega, okay, will be your x1 of omega, right? Similarly you can identify, so this is your x1 of omega, right? So similarly you can identify the Fourier transform of x2 of n, right? So the Fourier transform of x2 of n, I will indicate it as x2 of omega. So it is Fourier transform of x2 of n, right? So again it will be summation n is equals to minus infinity to infinity x2 of n into e to the power minus j omega n. Okay, this is nothing but your x2 of omega. So this x2 of n will exist only for negative values of n. It is a to the power minus n. Okay, so I can directly modify the limits here. So I will take only negative values of n. So n is equals to minus infinity to minus 1 will be there, right? So only negative values of n will be specified. So for negative values of n, it is a to the power minus n into e to the power minus j omega n. Okay. So here I can replace n with minus k. Okay. So to change these values to positive, right? So simply it will be k is equals to 1 to infinity, right? A to the power k, I'll take it as a to the power in place of minus n, it will be k, right? And e to the power j omega k will be there, right? So again, if I take this k is equals to 1 to infinity, if I'm taking k common, so a into e to the power j omega whole raised to the power k. So we have also seen this series, that is for n is equals to 1 to infinity, a to the power n is there, so it can be replaced with a upon 1 minus a. So if it is 0 to infinity, so it is 1 upon 1 minus, and if it is 1 to infinity, it is a upon. So we have seen this when we have seen Z transform. Okay, so here I can directly write it down as this x2 of omega is equals to a into e to the power j omega whole upon 1 minus a into e to the power j omega. Okay, so this is nothing but the x2 of omega, right? So as per linearity property of Fourier transform, what we have, the x of n, we are taking it as x of n is equals to x1 of n plus x2 of n. Okay, we are represented as linear combination. X of n we are represented as x1 of n, x2 of n. We will have the Fourier transform, which will be indicated as x of omega, and this x of omega will be simply x1 of omega plus x2 of omega, right? So therefore the Fourier transform of the given signal x of n is, so this is the required Fourier transform of x of n, that is nothing but x of omega. So we'll simply sum these two values, that is x1 of omega and x2 of omega, right? So x1 of omega is 1 upon 1 minus a to the power minus j omega. Okay, so it will be 1 upon 1 minus a to the power minus j omega plus x2 of omega is a e to the power j omega upon 1 minus a to the power j omega. So a e to the power j omega upon 1 minus a e to the power j omega. Okay, so if you want, so you can simplify it, otherwise you can keep your answer to this point, right? So this is the required Fourier transform of x of n. X of n was a to the power mod n, right? So this is how you can apply the linearity property to identify the Fourier transform. Okay, so in next session we will be discussing another properties of Fourier transform, that is time shifting and time reversal. Okay, so we'll see those two property in next session. Okay, so thank you for joining this session.